Arcurve is a Calgary-based technology company that's worked with several of the major players in Canadian industry, people from Shaw to TC Energy. We've had 800 or more successful projects in our history, and it often feels like we've resolved 800 unique issues with each of those problems. But that isn't usually the case. Usually, there are common threads between these issues, and there is one that is the most common above all else. That is what we call ETL. This stands for extraction, transferring, and loading. This is the process by which a developer pulls data out of an inconvenient resource into a much more convenient resource so they can develop a tool around it and do common sorts of analysis. And with steadily increasing frequency, we've realized that a lot of the ETL that we're doing is coming from one niche, one industry, which is real estate data. Now, I'm not talking about residential or personal real estate, but commercial scale real estate, data from the fields of architecture, engineering, and construction. These data typically come in the form of floor plans, architectural diagrams, or three-dimensional models that you often see in programs such as Revit, Rhino, SketchUp, or others. We see these data so often that I can say with fairly high confidence that many of your clients or your companies have access to this sort of BIM, business information management data, right now, and they just aren't 100% sure how to leverage it. This talk is going to be an exploration of how one could leverage that data. Specifically, we're going to turn a Revit model into a real-time Metaverse-style 3D interactive application, which isn't just for fun, but solves a practical business problem. We're going to, of course, demonstrate this in a more familiar context, though. I'd like to simulate a client proposal for you, and together we're going to unpack and solve all of these clients' problems to create such an application. So, in our fictional world, our client is an education board, which has recently developed a high school. This client's architects and engineers have collaborated in Revit to create a 3D floor plan that's going to be used during the construction of the project. Now, the client has invested a significant amount of capital into the development of this model, and they don't want it to go to waste now the construction is complete. So they've come to Arcurve with a proposal, a pretty challenging one too. The client wants us to create an AR/VR mobile application based on their Revit model, which, among other things, is going to keep each of their students safer by helping them simulate how a COVID cough is going to travel through the air ducts. Additionally, this AR/VR application should show in real time which rooms are at the highest risk for COVID transmission based on specific airflow information of the building. Now, this example is going to be unique to real estate management and real estate development, but the process that we're going to describe isn't unique to that space. Rather, we could take these same methods and build 3D models that are interactive for any data which uses a coordinate-based system, so any 3D or 2D data. Some examples that we want to bring to your mind as you're thinking about this or walking through this with us would be creating a warehouse application that uses AR or VR to manage stock and optimize the position of objects, or an interactive map that helps healthcare providers determine which location on the map would be ideal to place new buildings. Another one that we've talked about behind the scenes pretty often is for the mining industry. Mike Morley, a sponsor of this project from Arcurve, had often talked about how he would run airflow simulation analysis and structural analysis inside of mining shafts for different companies. These sorts of fields are all relevant to this work, and I'd like to ask you to keep those in mind as we continue to navigate through this one high school example. All right, so this problem we've proposed is pretty challenging. It definitely requires us to access data in an inconvenient format and then run airflow analysis on that data, not typically an easy job, and then to render the results of that airflow analysis on a 3D model on a mobile device, all in real time. Every single part of this sounds insane, but with the current technology that's out, it's actually reasonably achievable. So while solving this problem, we're going to step through 4 points and just chat about them as we do. First, we're going to introduce Revit and motivate why we have to extract the data whatsoever. You can already see a 3D model. We have to motivate why it can't be in that format. Number two, we're going to actually extract these data into Neo4j, which is a graph database, and we're going to demonstrate the benefits of doing so. Third, we're going to extract the data into Unity and create a custom C# application to process the data changes that we see inside of Neo4j. And finally, we're going to demonstrate the AR and VR capabilities of this process. After we do this, we're going to conclude that our client's business information management data is more accessible and extensible than it ever has been, and that the market is ready for applications that rely on these data. All right, so let's jump right in. First, what is Revit? Our fictional client said that they store their data in Revit. This BIM system is commonly used by architecture, engineering, and construction professionals to collaborate on complex models. And again, while we're focusing on Revit, the same process here is going to apply for Rhino, SketchUp, Navisworks, or BIM 360. These are all similar products used for the same purpose. Now, if you haven't worked with Revit in the past, there's two things you need to know about it. The first is the fidelity in these renderings is typically completely exhaustive. That means that every single outlet, railing, air duct, door, and wall is represented. And these are usually represented correct to the real world representation, since these models are used in construction. Second, every single element on screen or as part of this model contains metadata. This metadata is critical for our client's application, specifically in our case for the air ducts, which contain values such as the Reynolds number or the estimated cubic feet per minute that will help us do that airflow simulation. Now, if you're a developer in the audience, I'm sure you're going to see right away what the biggest issue is going to be, at least the first issue, and that is ETL, the extraction, transferring, and loading into a useful format. Now, before we jump into that process, I'd like to justify why we need to do it. There are two major reasons why ETL is the biggest step for a developer, the first step. Those are flexibility and expertise. For flexibility specifically, these BIM services like Revit, they're created with developers or designers in mind, and developers are certainly an afterthought. The software doesn't allow developers to easily access the code that draws models on screen, and therefore it's very difficult for us to customize a solution based around the data as we see it inside of Revit. For expertise, R-Curve's developers have expertise in almost every single programming language and framework that exists. And if we choose to abandon that knowledge and dig into just strictly Revit, which is certainly not a programming language itself, this is going to cost time, reduce the quality of the product, and not leverage the years of development experience that we've attained at R-Curve. So just to clarify the point and a fun little idea here, we don't know anybody who's a Revit data structure expert, but we know many, many people who are C# experts. We'd like to use them to our advantage. I'm going to pass this off to Eric, who's going to continue to talk about this process.
Awesome. Thanks so much, Andrew, for that excellent introduction and problem space setup. I just want to take this chance really quickly here to thank everybody who's here listening to this talk and join in on this discussion. It's great, and I'm glad you're with us. I'm super excited here to share some kind of more in-depth insight into the data sciencey world, which is, thanks Tim for those questions up front, because it was a perfect segue into kind of this section that I'm doing here. So I'm going to spend the next 15 or 20 minutes here to walk through the kind of what I'm going to call the data science software development cycle. As a data scientist for R-Curve, I'm often tasked with the responsibility of designing system architecture, analyzing the data, designing a solution to the problem, and implementing it. Obviously, this is a lengthy process, but we're fortunate today. With the selection of our stack, I'm actually able to walk you through an abridged development lifecycle here. Also taking a bit of a risk here, breaking the cardinal presentation rule. I will attempt this as a live demo, so word of warning, there may be hiccups, hopefully not. So let's wish me luck and let's dive in here. Just to kind of continue where Andrew had left off, is that the real first step that we have to do here is the ETL step. And in terms of Revit data structure experts, we don't have Revit data structure experts in R-Curve, but fortunately we know somebody that is one. And so we leverage this expertise of our Revit data structure expert. And he had actually pre-written some libraries to export Revit data to an arbitrary database. So I want to take this opportunity here to give a quick shout out to Will Reynolds for support on this project. Without him, none of this would be possible. There's his LinkedIn link. Very interesting individual. Anybody that's going to call himself a graph database addict is definitely somebody that I'm interested in speaking with, and I'm sure lots of you will find him interesting. Before I dive into the actual development process, I think it's kind of important to take a step back, get a little bit of a bird's eye view of what we're looking at here. So whenever there's data, it has to be stored in some format. It could be flat files, it could be in a relational database, or it could be in a graph database. It could be, it could be PDFs somewhere. In any event, it has to be stored in some format. The two we're going to focus on here right now are graph and relational databases. So there's an important distinction to make here between graph databases and relational databases. In a relational database, there's a kind of a predefined structure that shows the relationship between the entities. And that's generally what we call the schema definition. In a graph database, however, all of the relationships, which are called edges, are stored between individual entities. And there's no real predefined structure on how these edges have to be defined. So really, what it is that this is inherently kind of a more physical representation of real world things. Now I have a little example here. I'm not sure if you can see my mouse on the screen. Oh, you can, kind of. All right. I have an little example here where the green circles are what are called nodes. Well, the circles are what are called nodes. The green circles are people, and the blue circles are animals, pets. And it's kind of just, if you take a step back and look at it, it's very intuitive representation of real world relationships. In this case, we have Sam, who's married to Terry, who's friends with Wade. Sam and Terry have a dog. Sam's in charge of feeding the dog, and Terry's in charge of walking the dog. And apparently the dog is in charge of walking Terry as well. So this is kind of like a really simplified version of a graph. What we have here, while it's limited, it gives us very important insight towards the power of a graph database. With this picture here, you can ask very natural questions. You can ask a question like, who walks their dogs? And with Neo4j, they've created a language called Cypher, which is the query language into their database that's designed around kind of ASCII art. It tries to make a visual query. So with this first query, you can see this, the round brackets represent the circles, the nodes. The square brackets represent the connections with the lines in between, and the round brackets again here are the nodes. So even to somebody who's never seen this query before, it's actually quite readable. And what it's asking is, show me all people that walk dogs. And so this query here will simply return Terry. That's a relatively straightforward query. It would work just as well in a relational database. But where we can demonstrate more power of this graph database is to ask a kind of a more complex question. That question being, how does Wayne know Terry? Now, in a traditional relational database, this might be possible, but chances are that type of relation hasn't been set up. In the graph database, since every edge is modeled in here, we can ask it, well, pick this person Wayne and this person Terry, and find me the shortest path between these two, as in how do they know each other. And what this query will actually return will be a path from Wayne through Sam to Terry, and it'll say Wayne is friends with Sam, who is married to Terry. Now, that is where the real power of graph databases comes in. It's not to say that a graph database is the solution for everything, which it absolutely isn't. A relational database is really good when you have structured data. You know exactly what you're going to get, and you can already pre-optimize it so that your queries run well. On the other hand, if you have kind of a more real-world, dynamic relationships going on, you're not quite sure how it's going to be represented. You might need to add new things to the database later that you didn't necessarily consider to begin with. This is where having a graph database is really, really useful. So I'm going to kind of continue on with this bit of a philosophical discussion, I guess you can call it, where why would we use graphs in Neo4j? And I've already alluded to it, but I mean, in terms of this specific problem, we're asking a seemingly simple question, and it's how is the network of air ducts connected throughout the school? Now, that sounds like an easy question, but when you go down to try to write a program to solve it or implement some sort of solution, it turns out this is like, you know, our data's in Revit. We don't know how to do it. Like, how do we connect things together? How do we pull everything out? And it turns out that, excuse me, the answer to this question is actually very naturally represented in a graph database. And actually, it turns out that there's a lot of areas that are naturally represented in graph databases, and those are things like pipeline flow modeling, supply chain analytics, municipal planning. All of these types of processes have inherent relationships built into them, where if they are implemented in a graph database, you can pull out powerful analytics and powerful insight out of them. But that's enough of the kind of philosophical discussion here. We're going to jump into this software development lifecycle. So in terms of the data science software development lifecycle, I like to break it down into a few steps. And each step on its own is very interesting, has all kinds of ramifications. There's lots of work involved in each step. And so I'm going to try to kind of summarize it, make it nice and quick and something digestible for you guys to look at. So the first step is always data discovery. You know, you get all of this data and you say, well, geez, what am I looking at? So with Neo4j, they provide a very nice kind of browser viewer. And it provides an interface into the Neo4j database. This would be kind of similar to SQL Management Studio, where you can plug in queries and it spits out results. But on top of that, there's also kind of a graphical interface, which is really interesting to look at. So I have a few pre-programmed queries, which, you know, are similar to the queries that I showed you in the past or previously, but just a little bit more to them. This first query is very slow, so bear with me. We're not going to hang out here too long because with the presentation going on and everything running on my computer, it's definitely not very happy at the moment. But what I did right here was take a subset of the graph database that's here already. And what this query asks, and you know, we can look through the query and it's actually quite intuitive to read. We're looking for spaces that have terminals with airflow to equipment, basically, is all we asked. So all that I asked here is that show me all of the ductwork within this building. Now this query ran extremely fast. So there's a couple of, you know, very important points that we have to note here. This Neo4j database is a full representation of the Revit drawing. That means, as Andrew had said, it's exhaustive. It contains electrical boxes, electrical wiring, doors, floors, windows, in addition to the ductwork and all of that. Everything is linked here. And with Neo4j, you're just able to say, well, just show me the ductwork. Let's see how that works. Specifically, there's about 7,000 nodes in this Neo4j graph database that we got exported from the Revit model, and about 45,000 relationships. So these queries run extremely efficiently and extremely well. The other thing that I want to kind of mention here is that in a BIM model and a Revit model, they're used to build the building, and then they tend not to get updated anymore because they're a little bit clunky, they're difficult to use, the expertise isn't there from everybody to update it. In the case of this Neo4j database, it's actually quite easy to use. It inherently contains every little bit of information that's in the BIM model in this database as well. So it is a one-to-one representation of that Revit drawing. So updates actually that are made to the building can be made in this Neo4j database. Let's say the ductwork gets rerouted, change it in the database, and then all of your calculations are automatically updated. So given this dynamic nature of the graph database, it's actually in the end user's best interest to keep it up to date and use it so that they can continue pulling insight out of their data. So I'm going to simplify the query here a little bit so that we're not bogging down my computer. And now I'm just going to run the same query, but now I said, well, instead of all the ductwork, show me just the ductwork on the first floor. So now it runs much better. Oops. So now it runs much better. And so now you can see kind of how the ductwork works on the first floor. And you can see that there's spaces that are interconnected. And this is an amazing tool for data discovery. This is game changing. A lot of the times, data discovery takes weeks, takes months, takes a long time. The second we had transferred the BIM model into Neo4j, I was able to pull this insight out almost instantly, which is amazing. Just to kind of give you a quick tour of what's going on here, I'm going to zoom in and explain what each one of these things are so that it's a little bit less confusing. I know it looks a little bit like a mess, but just it's a network of ducts. I've been looking at this for a long time, so it all kind of makes sense to me. So everything in every one of these blue nodes is a space, is what's called a space. So it's like a room. It's here. This one's called a corridor. This one over here is called a cafeteria. And you can see each one of these green and gray parts are what's called are just parts of the ductwork. And then the connections are the actual physical ducts. And you can see that there's properties on each one of these elements, on the nodes and on the edges. And in this case here, for this edge, we have flow and we have the length of the duct. So that kind of takes us through that data discovery step. So now we can see here, oh, this is how the ductwork is. And oh, look, this is an interesting case here. So now that we've done this data discovery, we can kind of drill down and say, well, let's look at these two spaces in particular. So now I can run a query that will say, and note each time I run these queries, because they're drilling down deeper and deeper, they run faster and faster. We can run this query that will show us, oh, look, here's all the ductwork between the corridor and the cafeteria. Now this is exactly what we're looking for. Here we have a special case, and now we can start developing algorithms to solve the problem. So at this point, this is kind of like, I'm happy. We know where we're going, we know what we're looking for, and now we have a specific place where we can try to solve the problem with. So this diagram here still looks kind of complicated. The nice thing about Neo4j is that there are a bunch of plugins that have pre-programmed algorithms. In this case, if any of you are familiar with graph theory, we're going to use the good old Dijkstra's algorithm, which is a method of finding the shortest path between 2 points with weighted edges. So basically, what I'm looking for here is how do I get from here to here through these paths in the shortest distance. So that will be the last query that I have here. So now, this is more or less our kind of proof of concept. Here we have the query that says, okay, from this space, this corridor, to this space, the cafeteria, show me the shortest path, how to get there, and what is the length of that path. That is basically, for a watered down version of what we're trying to get at here, that's basically all of the information we need to calculate how long a COVID cough will take to travel from the corridor into the cafeteria. So, jumping back and forth here. So now we've done the data discovery and we've kind of done the solution development. We've isolated a subset and we found a solution that's going to work for us. So now we have to go to the implementation stage. Now, initially, I wasn't going to include this in the presentation, but it turns out with Neo4j and Python, armed with those two tools, it's actually a very small next step to take. So why not show it? So as the last step here, I've coded up a really quick example of how we can use Neo4j and Python to solve this problem for us. So a couple of caveats that I want to say first here. This is very simplified version of the flow calculations. So modeling airflow through a space it's actually quite a difficult problem. So for the purposes of this discussion, we're kind of making a couple assumptions, like the cough is right beside a return. I'm treating it more of like a constant source, like as if you were to light a scented candle by the return. And then this will be more of a calculation of how long it would take for you to smell that candle in a different space. Other assumptions are like the airflow through the ductwork is laminar. Again, this serves to simplify the velocity calculations, and that the system's in kind of some sort of a steady state with the airflow circulating as it normally does. So with this little program, and I mean, I made it longer than it had to be, but wanted to make it fun. We have our little program that we can just run here. And within a few seconds, the longest process there is just connecting to the database. What you see here is, it's saying hello, YYC DataCon. Many thanks to Neo YYC Data Society and all its associated partners for putting on this amazing event. Thank you very much. And then it says shortest path between these two spaces is 15.8 meters. And the time for a contaminant to travel through the ducts at an assumed rate of 2 meters per second is 7.9 seconds. So about 8 seconds to get from the corridor to the cafeteria, which is a really cool result. So that's what we've gotten to. So now, this is a very simplified result. The fact is that there's all the information in this database. So we can actually extend this solution that we have now to do full computational fluid dynamic analysis, let's say, and we can derive more accurate results and get actual real world reproducible solutions to this problem. But now that we've kind of done the implementation and all of this, we can turn around, put this back into the Neo4j database, and then Andrew can now turn around and pull the information out and kind of model it and show the end user what it looks like, which is a super exciting part. Now I'm excited to turn the floor back over to Andrew here.
Thank you very much. I'll also need the ability to show my screen. Perfect. Great. So now that we have the ability to simulate our cough inside of Neo4j and a bit of Python with Eric's program there, we're going to need to represent these in 3D. And we explored a few options for how to represent these best in 3D. However, surprisingly, the technology which is best suited for this application for our client is Unity. For those who are not familiar, Unity is typically associated with video game development and is responsible for many of today's modern classics, things like Hollow Knight, Cuphead, and the untitled Goose Game. But their product suite isn't limited to video games. And in the last few years, Unity has been creating a suite specifically designed to help those in architecture, engineering, and construction to view their BIM models in real time using the same high quality rendering engine we experience in their video games. This product is called the Unity Reflect Viewer. Now, for our purposes, we're not going to be using the viewer, but we're going to be using the Unity Reflect codebase itself. We're going to turn this Unity Reflect codebase into a custom application that connects directly to our Neo4j instance and updates dynamically based on the visualizations or the data that Eric has provided us. For those who are in the technical background, Unity Reflect is available on GitHub, and you can just fork it to create your own Unity Reflect application. There's several benefits for doing so. First, out of the box, Unity Reflect supports streaming data from all 5 of the major BIM services. These are Revit, BIM 360, Navisworks, SketchUp, and Rhino. Streaming these data is extremely advantageous for our application since the end user doesn't have to have the entire model stored in memory. This is going to allow us to support low power devices such as modern-ish phones. Second, Unity Reflect is a C# application written inside of the Unity platform as if Unity was an IDE. Now, the advantage for doing this is that we get to use a mature programming language like C#, which has libraries already that allow us to directly query Neo4j. We can also write any custom logic required to help out our application. Now, the final benefit of using Unity to develop this project with the Unity Reflect platform is that we can export to any platform that Unity natively supports. That includes Android phones, iOS phones, Mac OS, Windows, and on each of these devices, if the device has support for VR and AR, then we're going to, by default, have support for that feature. All right. So this right here is a preview of what you're going to see. I am going to show you a demo of Unity Reflect, but I do want you to see on the left what the data looks like to start with. The left-hand side here is a screenshot from Revit. It carries all the same model as the image on the right from Unity Reflect, but there are instantaneous advantages that you can see before I even open Unity Reflect. Of course, these advantages are purely visual, such as perspective rendering, dynamic lighting, but there are many, many more benefits underneath the hood. This right here is Unity Reflect. It is our custom application. A lot of the features and tools that I'm going to show in the next minute, just as I introduce Unity Reflect, are included by default inside of the forked project. And the added features you're going to see in the slideshow, because I'm less ambitious than Eric and I don't want to break that cardinal rule of presentations. So by default, when we stream an object from Revit directly into Unity Reflect, we get a lot of major advantages. First, we can toggle on different parts of our building and see how they work in real life or how they're connected to each other. Second, we mentioned at the beginning that it's extremely important for our application that our model carries all the metadata from Revit into the 3D model, as well as into Neo4j. On the right-hand side here, you can see that when I click on this window, I have all the same metadata that we have inside of Neo4j inside of this 3D renderer. And finally, but also certainly not a small benefit here, is that it's extremely easy to navigate around this system. If anyone has used a 3D modeling software or specifically Revit, you'll know that it isn't the most convenient to do fly-arounds or walkthroughs, but in this case, it's easy enough that I could do it with an Xbox 360 controller. Now, each of these are convenient benefits, but the real power is when we connect this to a custom application inside of Unity written in C#. Now, this is some work that I'm going to switch over to a slideshow for. Where I was able to connect our Unity model directly to the Neo4j database and to make queries based on UUIDs for specific objects. In this case, I was looking for the UUIDs of the air duct, which Eric had demonstrated in his work, where an individual will cough by that air duct, and we're going to follow the path that the COVID cough or the transmitted candle scent is going to go throughout the model. All right. So in this simulation, what I was able to do was press Y on my Xbox controller to simulate a cough. This would then send a signal to Neo4j, projecting where I am inside of this model. Then Eric's simulation would run, and we would determine which air ducts and which rooms would be affected within this cough simulation. I was then able to follow that cough to the room where the space, where the, sorry, I was then able to follow that cough to the room where the cough ended up. In this case, we see that it's the same cafeteria that Eric had modeled prior. Also using Eric's work, we're able to achieve another thing that our client had asked for. They had asked for a real-time map of all the locations which were high risk for COVID transmission within their building. By sampling several different points within the building and simulating a cough at those locations, then weighting the results of those coughs by the number of people who would pass through that space at any given point of the day, we were able to use Eric's work to estimate the highest risk locations for COVID transmission. This is the sort of data that our client is going to be able to use to make modifications, in this case to the entryway where there's a high risk of transmission, to ensure that its students are at a lower chance of risk or a lower risk. Simple thing that they could do is either place or encourage students to wear masks when walking through this area. Now, the final benefit here that our client asked for, the final benefit of using Unity, which our client asked for, is the ability to work in AR and VR. Given the platform and the way that we're presenting this to you guys, it's going to be a little difficult for me to show you this working. So what I've done is I've grabbed a video from Unity demonstrating this for the same building, but for a different application. And I'm just going to keep them muted as I talk through what they're doing and how this would also work natively inside of our application with no additional effort. So what they're doing in this is they are scanning a marker inside of a room, which is going to, if I crack open Unity here, be an option that we have available to us. I believe it's right here. So if I was to upload an AR marker, then I could do the same thing on a tablet, phone, or AR-enabled device. And what this will do is load the model around him. Right now, we're seeing that he is currently standing in the highest risk location for COVID transmission, so it's too bad he's not wearing a mask. He's in the lobby of the high school looking around and interacting with this data in real time. The device he's using is not a high-powered device, it is a tablet. The same thing would be true for our models as well. So this talk has been an exploration of what we can do with our clients' real estate data. In our conversation, we leveraged a 3D Revit drawing to generate an interactive Unity COVID cough simulation. We then extracted this, we did this by extracting the data into Neo4j for analysis and Unity for dynamic live rendering. However, we're also proposing that any data which uses 2D or 3D coordinates could be presented in an interactive Metaverse style application, but one that solves a practical business problem. We're also proposing that we're at a stage in technology where our data could be extracted into any modern framework and answer any challenging questions that our clients might have about their coordinate-based data. Now, we've already alluded twice here, but I do want to reinforce that this is not limited to real estate or commercial development. This could be brought into industries as diverse as supply chain analysis and dynamics, environmental impact simulations, city planning, or airflow dynamics. Anything that, the only thing that we're limited by is our creativity. Because of all these new technologies, it's a very exciting time for developers and clients to ask what they can do with their coordinate-based data. I'd like to thank you all for paying attention here during our talk, and I also want to give a special shout out to Mike Morley and Peter Tunkus at Arcurve for their support on this project. We invite you, the audience, to reach out to us at Arcurve if you have any questions that we can't answer in our Q&A here.